So good evening all of you. I am Chandrasekhar from the Orion Astronomy Club. Those who have been regular in our programs might have seen me. This year we didn't have too many programs. Usually we have several things going on around the year, but various reasons we could not do much. So we thought we'll have something like a big bang. So we have a very interesting program today. And our speaker today is Professor Rajesh Gopakumar. He is the director of ICTS. Some of you, I'm sure, would have attended the outreach programs conducted by ICTS, like the POPI program and other programs. So you would have seen him, met him, heard him. For those who are not, they have a huge campus about 60 kilometers from here. It takes a long time to go there, but I think it's worth going. I have not visited, though I tried a couple of times. So we should actually go there. It's a wonderful campus. I've seen on photographs. Looks very impressive. Professor Gopakumar, he did his undergraduate degree from IIT Kanpur and then went on to do his PhD in Princeton University. He was a research associate in Harvard University, and then he became a professor of Harish Chandra Research Institute in 2001. He was also a visiting member at the Institute of Advanced Studies in Princeton between 2001 and 2004. Currently, he is the director of ICTS in Bangalore. His interest is in theoretical physics, primarily in the intersection of quantum field theory and the string theory. Okay? We all heard about these terms, though we don't understand too much about it. Today we will get to know quite a few of that. So we are all looking forward to his talk. He also has a string of awards and recognitions, for example, ICTP Prize in honor of G.C. Wick, S.S. Bhatnagar Award, J.C. Bose Fellowship, G.D. Birla Prize, and the list is quite long. I'm not going to go through the whole thing. He is also a fellow of many prestigious organizations, like for example, Indian Academy of Sciences, the World Academy of Sciences, and so on. Okay. We are all eager to listen to him about Stephen Hawking's legacy and his contributions. Right? Stephen Hawking, of course, does not need an introduction to anyone. We all know, and we all probably have read some of his works. Today we are going to hear from an expert on what exactly was his contribution and how it stands in today's modern physical world. Okay, so that's what we are eagerly waiting for. Over to Professor.
Thank you very much for that very kind introduction and for the invitation to come here to your beautiful campus. I mean, it's my first time to the Infosys Campus, and I'm very impressed. I'm also very impressed that so many of you have showed up at 5 o'clock on a working day instead of doing something else. So it's very heartening to see this interest in fundamental physics, the kind of topics that I will touch upon. As you will see, there's a small connection also, and I'll come to it at the end, between Stephen Hawking, Infosys, and ICTS, which I will mention at the end. But actually, this photo is in fact from Stephen Hawking when he came to India in 2001, and so I'll again come back to that at the end. So what I will try to do is to give you a little glimpse of why Stephen Hawking's contributions were so important and continue to play a very important role in modern theoretical physics. So I will try to place it in a larger context. I've tried to make the talk very non-technical, but I'm very happy to people even asking questions in the middle of the talk. So if there's something not very clear, please feel free to stop me. There will be anyway a question and answer session at the end, but if something is not immediately clear on a point I make, please do stop me. Stephen Hawking, of course, all of you have maybe some of you have read his books, many of you have know his story. He was certainly one of the best known living scientists of the last few decades, and he passed away in March last month. And of course the story of him as a brilliant scientist who was trapped in this failing body, but yet managing to go beyond it, is something genuinely inspiring, and I think that's something you all know about. I won't dwell very much on that aspect. I will dwell more on his science. But you can see, I mean, how these pictures sort of show you how, as from a youth to the childhood, but then gradually he was confined more and more to his wheelchair. This is when I first met him. It was in 2000 or so in Harvard, when he had come to spend about a month in the research group I was in, and he looked a bit like in the left-hand side in that picture, and then of course I think the picture on the right-hand side is what is more in his recent times. But it is of course incredibly inspirational to see him also at close distance, and how he was functioning at the time when I saw him at close quarters. He was just able to move a finger and his eyelids, but he was communicating. He was even, one of our professors at Harvard had a party at his house, and he had come, and we were all enjoying the party. He was even dancing with his wheelchair in some sense to the music, turning around his wheelchair to the music. So he was that kind of person. But he, of course, addressed some of the most profound questions of physics, and some of the most important contributions that he made. Of course, his scientific career lasted, he started in the late 60s or mid 60s, and then he had even a research paper a couple of months ago before his death. So he had a very long research career despite his increasing debilitation. But his most important contributions were in the 1970s, and the ones that I will more or less focus on. And a recurring theme in his work is about the properties of black holes, and even to some extent on the Big Bang. I will mostly focus on the black holes part of it, and try to give an idea of what the significance of his work is. So let me place this in a larger context. As part of the journey of physics. It is a journey which, starting from our everyday life, in a way it takes us to the very, very large, but also to the very, very small. And one of the things that Hawking's work also uncovered is some of the surprising connections between the very, very small, the physics at the very, very small, to the physics at the very, very large. And I'll try to explain how that comes about. But just to sort of, all of you know this, but what is physics about? The physical laws are basically aiming to understand the regularities and the hidden patterns, underlying patterns of nature. And this is what we do even when we study the laws of physics in high school. As all of you have presumably done, you learn about how things move, what kind of how to predict the position or the velocity of some trajectory, or you study electricity and magnetism and try to understand how currents are generated by moving magnets and so on. So you try to understand these regularities and underlying patterns of nature through physical laws. And what is quite remarkable is that we have been able to do, mankind has been able to do it in very precise mathematical terms, and it continues to be so. Even as we widen the scope of these laws, we go away from the daily experience, we go away from trying to describe how this pointer may move under the acceleration due to gravity. We go to regimes which are far removed from our day-to-day experiences, either at the very large scale or at the very small scale. So even as we widen the scope, we find there are physical laws, there are patterns and regularities which we can describe in precise mathematical terms. So that's the quest of physics, that's the journey of physics. And as we'll see, Hawking played an important role in our understanding of some of these connections in this journey of physics. So let me start by placing it, as I said, in a wider context with something all of you are very familiar with, which is the force of gravity, which will actually be the sort of the central theme of this talk as well. So gravity, all of us know, even as children, we try to stand up and fall down, we feel immediately, I think probably one of our first experiences as humans is knowing that, oh, if you fall down, you'll hurt yourself. So there's a force that's always bringing you down the stairs or bringing you, if you try to climb up or jump up too high, it's always acting against you. So it's in a sense the most visible force in nature. But it was Newton who had the insight to realize that there is a law of gravitation. There's a way to describe the force of gravity in a very universal way, and this is the thing maybe all of you have seen in your school textbooks long ago, that the force of gravity is something which is proportional to the masses, and it is inversely proportional to the distance between the two objects. And what was remarkable about Newton's idea was that he realized that this force should apply to let's say this bottle. If I throw it here on Earth, it applies to the force of gravity here on Earth. It also applies to the force of gravity that keeps the planets going around the sun, or Halley's comet coming and every 76 years into the solar system. They're all governed by the same law. And there is a universal constant, this G, which is the Newton's constant of gravitation as it is called. But apart from that, this law is very good. In fact, it describes very accurately the motion of planets, and even when ISRO sends up all its satellites, its rockets, or you have a spacecraft like Mangalyaan going to Mars, its trajectory is calculated using the laws of Newton. It's a very good description for most purposes in the solar system. But what you realize, and this is what in 20th century we have realized, is that as you go to the very large, as you go somewhat wider, as you enlarge your scope of your experience or your ability to see into the universe somewhat more, you will realize that Newton's law, which you learned in school, and maybe no one told you this, but it's actually only approximately true. It actually has a certain regime of validity. It is a sort of it is a very good description, but it actually is only approximately true. But in a way that shouldn't disturb you. It is in the nature of physical laws that they are true to they describe things within a certain domain, but they may be only an approximate description as you try to enlarge that domain. And this is true for the motion. It's true even for the Maxwell's laws that describe the electromagnetic phenomena. It is true for many of the laws. So in that sense, our understanding of physical laws grows gradually as we explore more and more phenomena. So let's see in what sense this is only approximately true. And this was the insight of Einstein, that he realized, and a very brilliant insight, that gravity is actually geometry. So if you had to sort of encapsulate his picture in 1 or 3 words, this is it. And of course, what does one mean by that? I'll try to tell you a little bit more, but this picture here is a kind of a cartoon picture, but a reasonable illustration of the idea, which is that whenever there is something massive, even you and me, but of course large objects like stars and planets and so on, they curve the geometry around them, the geometry of space and time around these objects are actually curved, in the sense like the surface of a balloon is curved, and so when you draw a triangle on a surface of a balloon, the sum of the angles of the triangle is actually more than 180 degrees. So curved geometry is is different from the normal plane geometry you study in school, and it has its own mathematics. The more generalized, it's called Riemannian geometry, but this the curved space-time can be described very precisely, and Einstein's insight was that, just like you see in that picture, the space and time is sort of curved, and so an object like that satellite in that picture is trying to actually go in the straightest possible line in that curved geometry, but it appears to in trying to do so, it looks like a circle or an ellipse, at least to a good approximation. And so it is the geometry that is shaping the motion of the planets or the sun or the any object under gravity. It's that curvature which is telling, or which is guiding the motion of objects. And there's a very precise mathematical way to do it, and you see Einstein's picture there writing the so-called Einstein equations. So as I said, Einstein just overhauled the very framework for describing gravity by tying it up with the geometry of space and time. So space-time was no longer some kind of a passive stage on which things happen. So when Newton and so on wrote his laws of motion, he assumed that space and time are just fixed forever, and it's like the stage. And then the drama of all whatever happens happens on that passive stage. But now, in a sense, the stage has become a participant and responds to the objects on it. So as I showed in that picture, the presence of a heavy object curves the stage. I mean, so it's this rubber sheet kind of picture that you put more massive objects, it'll curve the sheet even more. So space and time become much more dynamical, as they say. So Einstein's theory is in a very different mathematical framework from Newton's theory, as I said a little bit earlier, but it's in terms of what is sometimes called a metric, never mind what it actually is, but it is like you've maybe seen electric fields, magnetic fields. You talk of a metric field, which actually measures the distance and even how much space-time is curved. There are equations that Einstein wrote, just like Maxwell's equations, which determine what this metric is in terms of the matter. So as I said, if there's a lot of matter, it will curve the space-time more, and you will see that in the Einstein equations. And quite remarkably, this actually reduces to Newton's laws when the densities are small or velocities are small, but it is actually a more complete description, a more Newton's law, as I said, is an approximate description, but Einstein's description covers much more, many more situations. So you might ask, what is an example of a situation where you need Einstein's theory? I told you in the solar system, or for sending spacecraft to Mars, Newton's equations are sufficient. But actually, if you look, and this is what through telescopes and so on, and many of you are probably members of the astronomy club, so you know that there are lots of exotic objects out there in the universe that we have discovered. There are very highly dense objects. There are very fast moving objects. So like neutron stars are very dense. A teaspoonful of neutron star matter weighs as much as the Earth. So imagine how dense that is. So it's just a teaspoon, and it's the same mass as the whole of the Earth. So there are objects like that. There are very fast moving objects like these pulsars, which send out these signals milliseconds. Every millisecond it is sending out huge bursts of radiation. There are black holes, which I will talk about more, both of the mass of a star like our sun, but even much more massive at the center of galaxies. So the right hand side picture is a picture of a galaxy, and there are black holes which are maybe 10,000 times the mass of the sun, 10,000 to 100,000 times the mass of the sun. So there are enormous objects like that out there in the universe, and to describe them we need Einstein's equation. Once you start measuring their properties, you see that Newton's laws are no longer very good for describing, let's say, the motion of two such neutron stars around each other, or the behavior near a black hole. But I must also point out that actually there are even some things down to earth that Einstein's theory has a consequence for. So even in the smartphones, the GPS system that one has, that needs to take into account corrections from Einstein's equations for how the time is sort of slowing down at different points in a gravitational field. So the way the GPS system on these phones work is that they send signals to a satellite, and there are maybe 3 satellites which sort of pinpoint the location of your GPS. But the satellites are in orbit. They are further out in the gravitational field of the Earth, whereas we are on the surface. So the time that the clock here measures and the clock on the satellite measures is actually off by a slight amount. There is what is called the gravitational slowing down of clocks, or time dilation as it is called. And this tiny difference actually makes a difference to the accuracy to which you can pinpoint your location, because if you do not take that into account, the principle of the GPS triangulates your position based on the time it takes for the signal to go and come back. So you know the speed of light and you know the time, and so you try to measure distances that way. But you have to take into account the time difference between the clock that you have and the clock that is there on the satellite, which is why extremely precise clocks are used in doing a lot of these timings. But that very small correction, maybe 1 part in a billion, that can accumulate, and you can be off by a few 100 meters, especially if you want very high precision location, and many of these errors accumulate over time, and so you can be quite far off if you don't take into account this correction. So all that abstract, maybe mathematics and so on of Einstein has even an effect. It has to be taken into account when you are working with your cell phone. So this Einstein's picture of gravity gives, in terms of geometry, it gives a very highly successful description of the universe's evolution to the very largest scales that we know of right now, which is roughly about 1 million times the size of the Milky Way galaxy. So we know that our solar system is just one tiny little part in some backwaters of this Milky Way. So the Milky Way itself is just a spot in the whole universe, and this is a kind of a depiction of the various galaxies that are there. And there are of the order of nearly 1 trillion galaxies, and so we have explored the universe to about 1 million times the size of the Milky Way, and and Einstein's theory actually at this very, very large scale, the Macrocosmos, is a very good description. So you might think, oh, so we are quite done, and so even though Newton's laws are not valid, we have Einstein's theory. But actually the answer is no. Einstein's theory itself throws up some puzzles. And this is what you have when you study these objects called black holes. And these are in some sense the most very unintuitive or very mysterious predictions of Einstein's theory. And this is an image of, this is also just a recreation of a star and a companion black hole, and the black hole is very tiny compared to the star, but its gravitational field is sucking matter from the star, which is spiraling in, and that central black spot is the black hole. The rest of it is just the gas which is spiraling in. And how are these black holes formed? They are often formed by a star which has no longer has the energy to burn and generate energy, then it just collapses under the force of gravity. And this is in a sense what Subrahmanyam Chandrasekhar realized almost a century ago, that there's in the end nothing really that can stop collapse of a dying star, and the final product in many cases seem to be black holes. So it's something very dramatic, because the gravitational field of this black hole is so strong that space-time is so curved that even light cannot escape from behind a certain radius, which is why it's black, or we call it a black hole. Maybe you've heard there is something called the horizon. So if you are, and that's the sort of a sphere whose radius is proportional to the mass of the object, what I've called m. So it's a sphere whose radius grows with the mass, is proportional to this thing. That sphere is called the horizon because light from behind, anywhere in the region behind that horizon, cannot escape. The field is, the curvature of the gravitational field is so strong that it just pulls the light back in towards it. It's like light is, on Earth you have an escape velocity, To escape the Earth you have to send a rocket at some escape velocity, then only it can, if you throw up a ball, of course it'll fall back on Earth. But rockets and spacecraft manage to go have the escape velocity. So in a sense the escape velocity about this black hole is such that even light is not fast enough. So that's why you have this phenomenon. And how do you then see it if it is so, if light cannot escape? Well, you usually have systems like these where you have had, maybe originally at some point there were two stars which were rotating around each other, but one companion star collapses and forms a black hole, but then you see this kind of jets, there are vertical jets coming out, and there's a lot of high energy radiation coming out from near the black hole, so it's a very compact object which seems to generate a lot of energy, and so that's a sort of a signature of a black hole, and one of the first such examples was Cygnus X1, and this is so it's a companion star in the Cygnus constellation, and this is this is an artist's depiction of that, and that was one of the deductions. But now, thanks to gravitational waves, which you might have heard of, the detection by the LIGO detector in 2015, you can actually see direct signatures of black holes, and you saw the right-hand side pictures of a pair of black holes colliding, and perhaps you have read or heard about this marvelous detection, which is a direct way of now learning about the existence of these black holes, which I must stress again is a prediction of Einstein's theory and not something we would have known from Newtonian theory. Okay, so I told you about these very supposed seemingly exotic objects, these black holes, but why are they so important, and how do they enter into Stephen Hawking's story? So I'm now coming to that. So firstly, there are very special solutions of these Einstein equations, whatever they are. You can find these solutions, and in fact, the very first solution was found a few months after Einstein wrote down his equations, and which describes the most simple black hole. These are very highly symmetric solutions. In a sense, they're very simple in some sense, because once you specify the mass of that black hole and you specify how fast it is spinning around some axis, you basically completely have specified the black hole. So it's a solution which has just two parameters, the mass and how fast it is spinning, and then the solution is completely fixed. So it's a very, in that sense, very beautiful, simple, basic object in Einstein's equations. And then they have this thing called the horizon, I said, which is the region from which light cannot escape. But there's another feature of black holes which actually is also a very important feature, which is there is something called the singularity, which is hidden from us because it is actually behind the horizon. And this singularity is a place where actually the curvature in fact becomes infinite. And Einstein's equations themselves stop making sense because you're getting a solution which at some place is sort of blowing up, so to say, is just going to infinity. So that's actually something I'll come back to perhaps later, but it's a signature that you may need to go beyond Einstein's equations in some circumstances, like these singularities. So now let me bring Hawking into the story. So one of the first things that Hawking became well known for was in the late 60s, when he showed that this behavior where you have a singularity is something not just special to these very highly symmetric solutions of Einstein's equations. It is something that so many people used to say, oh, these black hole solutions are very special because they are just very symmetric things. In when an actual star collapses, it may not form a black hole, there may not be any singularity or any such thing. There were people who actually felt that black holes were not were just some very special things and not maybe realized in nature. But what Hawking, together with Roger Penrose, another very famous physicist, a mathematician, showed that this singularity, this behavior is actually something you can always, you will always find in any collapse or in any scenario which is the opposite of a collapse, like a big bang, an explosion. So either in a collapse or in an explosion, you will always, the Einstein equations will always end up with a certain singularity. And so this actually helped people to realize that black holes are very generic. They are very, you will come across them, and now we see that in nature. We see tons of black holes, and LIGO is just going to keep detecting they say, tens of black holes every year, black hole collisions every year. So there are likely to be millions of black holes in the universe. So it's a very, they're very common objects in that sense, and nothing very special. So one thing I wanted to stress is that this seminal work of Hawking and Penrose had an Indian connection. About 10 years before that, Professor Amal Rai Chaudhary of Presidency College in Kolkata had actually written down an equation using Einstein's theory, which played a very crucial part in this Hawking and Penrose's proof so these Rai-Chaudhary equations, as they are called, actually are very essential for showing that this kind of singularity is very generic, is something that you will see. So, so this was, in a sense, Hawking's first major contribution. But then he actually shifted his focus to studying black holes specifically, and this is where he made his greatest discoveries. So one of the first things he discovered was a very remarkable feature of this black hole horizon. So you remember I talked about this horizon, which is the region beyond which light doesn't escape. What happens if, say, two black holes come together, or some matter falls into a black hole? Some generic situation. Can you say something about this horizon? So one of the important results of Hawking, which he showed using Einstein's equation, was that the area of that horizon will always increase. Whatever you do, you can never shrink the area of a black hole horizon. It is bound to keep increasing. And this is was quite unexpected. You might think that maybe there's some clever way in which you can sort of, maybe a black hole will somehow spin, and some part of the energy will go away, and its area might shrink, or when a black hole and collides with some other thing, maybe that other thing will carry away some energy, so that the black hole might shrink. But it doesn't happen. What he showed was that this area, it's like one of those horror movies things. It just keeps growing and growing and growing. It will just and starts eating up everything around it, in a sense. So that was what is sometimes called Hawking's area law and area theorem. And he further, with others, he developed what they call the 4 laws of black hole mechanics. This name comes from something maybe some of you might have heard, the 4 laws of black hole, 4 laws of thermodynamics. Now, thermodynamics is something you study in school. It is about the science of heat. It's about how hot objects behave. And what can you say about them? So there are some of the basic, our understanding of thermodynamics is captured in the 4 laws of thermodynamics. And I won't go through all of them, but one of the, there was what they discovered was there's a very close analogy between what they were finding for black holes and for the laws of thermodynamics. Which at first sight are 2 totally different things. Thermodynamics, as I said, is about hot objects. How do the molecules of air in this room, if you're putting an air conditioner, how fast will it cool? How fast will something heat up? These are the things that thermodynamics studies. It has, at first sight, nothing to do with Einstein's equations or so on. But maybe if you have heard a little bit about thermodynamics, you might have heard of the 2nd law of thermodynamics. The 2nd law of thermodynamics is the one which states that entropy or disorder, which is a kind of colloquial, entropy is the more technical term, but entropy is essentially a measure of disorder. And this is the statement all of us in India are familiar, that disorder only increases. And you have to do something really difficult to make, have an ordered campus like this or something. You have to work very hard and put in a lot of energy to order things. But in general, our disorder only increases. This is a thermodynamic fact, and it is the statement of this entropy increases. So there was an analogy, at least. It seemed like similar. There's an entropy which is always increasing. There's the area of a black hole which is also increasing. Okay, 2 things that are increasing. But if it was just that, maybe, okay, many things might be increasing due to global warming. The temperature of the Earth is always increasing, so maybe, but that doesn't mean there's a connection between them. But they found there were other laws. There's the 0th law of thermodynamics, which says that if I bring 2 objects of different temperatures together, they will eventually come and be at the same temperature. There's the 1st law of thermodynamics, which is essentially the conservation of energy, which tells you heat can be converted to work and so on. And what they found was there are close analogies of all those laws with features about black holes. So as I said, thermodynamics is about things which have a temperature. What is the temperature? What is, the entropy? The analog of entropy is this area of the horizon. but the temperature in this correspondence that they noticed was related to the acceleration due to gravity at the horizon. So there's the horizon, and there's obviously an acceleration due to gravity there, which is pulling things in, as I said. And that acceleration sort of plays the role of the temperature, if you make this sort of connection. And area plays the role of entropies, if you make a sort of analogy with thermodynamics. But in what sense is this be a real temperature? So there's so these people, even Hawking and others, when they wrote this, it was said this is a very fun analogy, this is a very curious observation, but we don't know what it means, because black holes cannot have a temperature, because what is a hot body always radiates heat, right? I mean, so it sends out heat, and black holes, I just told you, cannot have any radiation. Radiation is sending out light or heat, any kind of transferring any energy through either electromagnetic radiation or some other radiation. But black holes, I just said, cannot emit anything. So, so it seemed like this analogy shouldn't make any sense. Now I want to take the story in a different direction. So I'll leave it at that. That it seemed like a very puzzling observation. So now let me introduce a new ingredient where we go to the very, very small. This is the realm of the small, and this and where we are talking of atoms, and the physics at that very small scale is due, the existence in fact of atoms is due to the quantum nature of the electrons and protons and that constitute the atom. And in fact, light itself at some level, we understand it as being a particle-like nature, having a particle-like nature, which is what we call photons. So there is, in quantum mechanics, there is this duality which is very nicely captured by this little cartoon. You can see, if you see it one way, it says light is a particle. Can you see that? P-A-R-T-I-C-L-E with an exclamation mark. But if you see it another way, it looks like a wave. So in a sense, light and matter actually has this dual property of, you see it, in some ways it shows a particle-like nature, some ways it shows a wave-like nature. And this is true for, and this is the intrinsic nature of matter at the quantum level, which you don't see day to day. I mean, you don't normally, when you do an experiment with light, you see only its sort of wave-like nature. But if you go to, if you have sensitive enough instruments, you can see individual photons. And in fact, again, the touch screens of our mobile phones and so on use the idea of the photons. And it's the basis of all modern electronics and gadgetry, computers, smartphones, touch screens, and so on. And someone actually estimated that 30% of the US GDP is based on quantum mechanics. If you didn't have quantum mechanics, if you didn't understand the quantum mechanical nature of matter, you wouldn't have any of this, and you know what that means. So, again, very abstract things. Like this, but have very consequences in our lives as well. So anyhow, so this is about the microcosmos to the very, very small, and we have by now, and this is a different story which I'm not really going into, but we have now explored things about 1 billion times smaller than an atom, and this picture is of the Large Hadron Collider in CERN in Geneva. You see the Geneva airport runways at the lower left-hand corner. So and that circle is the ring of the collider. So you can see the scale involved. But in these colliders, we have explored matter all the way to 1 billion times smaller than an atom, which is itself something like a billionth of a meter. So we have, and quantum mechanics describes the other interactions of nature, electromagnetism, the radioactive weak interactions, or the nuclear strong interactions, and so on. So this is something, is also a part of our understanding of nature at the very small. So the Einstein description that I talked about of gravity is a, so to say, classical description. It doesn't take into account its whole framework is within the classical framework, and it doesn't have quantum effects into it. In fact, Einstein discovered this before quantum mechanics was fully developed. So one of the things Hawking asked was, what happens if we consider a black hole in a quantum world, in a world in which you don't pretend that everything is classical, but realize that ultimately things are quantum. And that's what Hawking did, and he found to his surprise that if you really take into account the effects of quantum mechanics, black holes do radiate. Despite what I said, the picture that I said earlier is at the classical level, and in fact, to a good approximation, that is correct, and you don't see light. But if you take into account the quantum effects, they do radiate, and indeed they actually have a temperature, and they have an entropy, and he gave these very famous expressions for the temperature and the entropy. In fact, so the temperature you see has a factor of what is called H, the Planck's constant, which is showing that it's a quantum effect, and it's inversely proportional to the mass m and the Newton's constant g that appeared earlier. And the entropy you see has a factor of A, which is the area of the horizon. So indeed, the entropy increasing is the area increasing, because the entropy is proportional to the area of the horizon. So it was not a coincidence that the entropy was that the area was increasing, because it, in some sense, is really like the entropy of the black hole. So this is what Hawking, in a sense, is most famous for his understanding that black holes can radiate if you take into account the quantum effects, and they radiate at a very specific temperature. It's a very small temperature. If you put in a black hole for a black hole of the mass of our sun, this is a very tiny, it's like 10 to the minus 11 Kelvin, very small. So it's a small effect, but it's an important one for understanding what really black holes are doing. And in fact, this formula on the right hand side for the entropy is what is going to be embedded on his tombstone. He is going to be buried in a ceremony later this year at the Westminster Abbey in London, where all the famous British people of Britain have been traditionally buried. So next to Isaac Newton and Charles Darwin and so on, and he will have on his tomb that formula S equal to A over 4hg. Because it's such a fundamental discovery that he made, that black holes actually do radiate, but if you include the quantum effects. So let me say a little bit about the significance of this. Because entropy, I talked about, all of you are familiar with temperature, more or less, we all feel it. But entropy is something less, is maybe something you have less experience with or thought about. We now understand what entropy really means. When I said earlier about disorder, it is really coming from the underlying internal structure or internal number of configurations that object can take. So if you have a bottle of water, this has some entropy because there are many molecules inside it. They're all jiggling around in their own different ways. There are many ways they can do it and still have a total temperature which is maybe 20 degrees and a total volume which is this much. There are many different configurations that the water molecules can take, and that's what measures the entropy of the water. And this is the insight of the famous physicist Stefan Boltzmann, that entropy is the logarithm of the total number of states. The thermodynamic entropy can be actually understood in terms of the number of different states. And entropy increasing is the fact that things can be in more and more different states, and therefore the sort of more and more disordered, more and more everything is ordered. Then there's one state. If all the traffic is going in a straight line, everyone in their own lane with a fixed separation, that's a unique configuration. Everything is ordered. But if, like we have in Bangalore, traffic is going in many different ways, the total number of ways you can have traffic jams are many, many, many. So that's why there's a lot of, so this entropy is a measure of the disorder, and it's the number of different states you can have. So Hawking's result was very astonishing to the physics community, because in Einstein's theory, at least I said black hole is a very simple object. You tell me its mass, you tell me how fast it is spinning, and that's it. It's completely fixed. So it seems like a very ordered object. And so it seems without any internal structure, where is this? It should have had zero entropy. And so this is therefore Hawking's result was saying that when you include quantum mechanics, or really when you have a quantum theory of Einstein's gravity, then only that can explain the different states that a black hole can take and reproduce that entropy that Hawking found using very general arguments. So this has been a major challenge for theoretical physics since Hawking's discovery, that anyone wants to propose a quantum theory of gravity, they have to account for this entropy. They have to account for the so-called microstates of the black hole and derive the Bekenstein-Hawking entropy. Actually, Bekenstein was a physicist who, before Hawking, realized that the black hole should have an entropy proportional to its area, but he was not able to fix it completely. And it was Hawking who really did the sharp calculation and got the precise formula that I think, but it's sometimes called the Bekenstein-Hawking entropy, whereas the temperature is called the Hawking temperature because he's the one who actually derived that thing. So anyhow, coming back, the challenge for any quantum theory of gravity is to derive this answer of Hawking as the log of the number of states, so that it's a genuine entropy. And this is where string theory and some of the things that people in that subject, including myself, have been studying. String theory is a framework for understanding quantum gravity, and the basic objects are sort of one-dimensional extended string-like objects. Like this, I've shown a version which is like a rubber band. It's what is called a closed string, or you can have like a piece of thread. It's an open string. These different versions. But the important thing is, among the excitations of the string is the so-called graviton, which is the analog of the photon, and it is the quantum of gravitation. And so strings naturally describe gravitation at the quantum level. And indeed, it was shown in 1995 by Strominger and Maffa to string theorists how, at least for a large class of black holes, you can exactly reproduce Hawking's answer from counting the number of states that these strings can vibrate in, or the various objects in string theory can vibrate in. And moreover, you can actually find systematic corrections to that. That's the leading contribution to the entropy. There are corrections which which people after Hawking had talked about, and you can derive those. So string theory, that was a very major important step for string theory, and to be convinced that it is the right framework for studying quantum gravity, that it was able to reproduce that answer including that factor of 4 and everything, area over 4 hg. It's very non-trivial to reproduce that exact answer by counting as log of some number of states. And this is one of the things that string theory was very successful in doing, and by now in a large class of these black holes this has been done. So string theory, that's one of the things that, and that's why in a sense it has carried the legacy of Hawking forward in understanding Hawking's result in a very microscopic way. But you might think, okay, quantum gravity, is it something you need only for these black holes and so on? But no, it's actually even necessary to investigate the birth of the universe. The very small, at the origin of the universe, there were quantum fluctuations, and that's what actually gave rise to all the galaxies that we see today. And there's an inhomogeneity in the sky. Maybe you might have seen pictures of the so-called cosmic microwave background, and those two plots are actually of the cosmic microwave background on the top, and the structure of galaxies, clusters of galaxies on the bottom. They look somewhat similar. You see there are inhomogeneities. There are patches where there is nothing. There are voids, and then there are patches of high density. This inhomogeneity now we understand as coming from quantum fluctuations at the origin of the universe, and this is something, again, Hawking was one of the first people to observe this. So mostly, while I talked about black holes, quantum gravity is essential to even understand the very origin of the universe, the Big Bang. And this is what in this picture on the left-hand side you see. On the left side, it's a picture of the evolution of the universe. At the very left, you may not be able to read it. It says quantum fluctuations. At the Big Bang, the bright spot there. So those gave rise to all the galaxies we know today. The structure is explained because of quantum fluctuations. So anyhow, I'm now coming to the end, but one of the things I wanted to mention is how India has been playing a very important role in string theory, and in some sense, perhaps you know, or if you don't, it's something to be very happy about, that outside the US, perhaps the single most influential community of string theorists worldwide are in India. They're working in India. They're pushing the frontier of the subject in different directions, and the connections to cosmology, to the black holes that I mentioned, even to other seemingly different unrelated areas in solid-state physics or mathematics. And there are institutions, Harishchandra Research Institute in Allahabad that I was at, ICTS, and TIFR, the Tata Institute, our parent institute in Mumbai, and so on. These are places which have been pushing the boundary of string theory. And I just wanted to mention, maybe you've heard of the name of Ashok Sen, who's one of the pioneers who actually played an important role in setting the stage for the calculation of black hole entropy in string theory, this reproducing Hawking's work in string theory. And his work, he's at HRI in Allahabad. And so this is something, and this brings me to Hawking's visit to India in 2001. So at this main string theory conference, every year is held typically, usually in North America and Europe, but in 2001, for the first time, this meeting was held in India, in TIFR in Mumbai. And this is a picture from there of Hawking had come for this conference. So it was a sort of the reason the world's best theorists came to India was because of the Indian contribution to string theory. So you see Hawking in the middle is David Gross. In 2004, he got the Nobel Prize in Physics for his discoveries in the strong interactions, one of the most eminent physicists of present day. And maybe some of you have come for our ICTS events. He has given public lectures here at ICTS as well. And recently in January at the for the Christ University, there was an interaction with him and Mr. Narayan Murthy and others. And on the left is Edward Witten, who is a Fields medalist, the only physicist to have won the highest prize in mathematics for his, and he's one of the premier mathematical physicists of the world. And so a picture on the TIFR lawn of the three of them, I think, trying to read what Hawking is saying on his screen. And of course, he was the center of media attraction, and he gave visibility to Indian science at the frontier. He spent 2 weeks, I think, at that time. And so this is where, in a sense, I want to mention the Infosys connection. I think it was very expensive and very non-trivial task to bring him in his condition and with the support that he required and everything to India. But Mr. Shibulal, one of the founders of Infosys, was one of the people who had to, through the Sarojini Damodaran Foundation, to support his visit to India. And so he came, and it was, I think, a lot of very good exposure for Indian science and in the Indian media. I think he was quite a celebrity even at that time. And the other connection is that Professor Spencer Wadia, whom you might see next to Hawking on the right-hand side in that picture, was the founder-director of ICTS. He brought Edward Witten, who is there in both pictures in the same check shirt. He brought Edward Witten to Bangalore because he wanted to see the Infosys campus. So actually, right after the Strings meeting in 2001, Ed Witten and Spencer Wadia came to the Infosys campus with Mr. Narayan Murthy, and because he wanted to see the temples of modern India, so as he called it. So there was a connection in 2001 itself with this thing, and Spencer Wadia himself was very impressed with your campus when he saw it in 2001, and sort of has felt we should have a similarly beautiful campus in academia in Bangalore, and that was part of the motivation for him to try to set up ICTS. And I think we've now begun on that journey there. So let me close. I think I've probably gone through my time. So let me just close with an inspirational statement from Hawking. It's so I think it's clearly his life is something we will all be remembering for a long time, and especially for many of you, I'm glad that you came to sort of come and look at some of the things in the stars in the midst of our everyday life. So thank you very much. So feel free to ask anything, even if it's very elementary. Yes.
Yeah, my name is Vijay, and the question I have for you is, you talked about entropy as being the logarithm of the number of states. So does this mean that entropy for a natural system in the universe, as we know it, is always greater than zero, rather than being greater than or equal to zero?
It's always greater than zero. In fact, the third law of thermodynamics essentially states that you can really never have a zero entropy system, in a sense. Even in, I mean, the only way, or rather it actually states it in a different way, but it states that you can never reach absolute zero in any finite process, but if you could reach, it's only at absolute zero temperature that you could have had zero entropy, but you would not be able to, through any finite thermodynamic process, reach absolute zero. So indeed it is true that the entropy is always greater than zero, and the increase of entropy can be greater than or equal to zero, but yeah, you can never exactly have zero entropy in any system arrive at, except at sort of the absolute temperature equal to zero. By the way, I mean, since many, I don't know if what your backgrounds are, but this is very related to things in information theory. In information theory, Claude Shannon, the founder of information theory, measured information in very similar ways. Actually, the Shannon entropy is a very close analog of the thermodynamic entropy. And currently people are actually exploring the relation between this Hawking's entropy and Shannon's entropy in some way. And and people talk about quantum computation and quantum information, and these subjects are actually related, so you never know. Hawking's work may play a role in your life a couple of decades from now, because it might enter through quantum information theory. Yes, please.
I have one more question, and then I promise to shut up. In quantum physics, essentially the whole concept of a wave came from the work of Fourier, at least as far as I am aware. And one of the laws over there is that for a time-limited signal,
the Nyquist kind of theorem.
The spectrum is unlimited, and
there's a delta in the frequency, uncertainty in the frequency and uncertainty.
Right. So my question then is that do we have this wave-particle duality because we are using a particular tool to model, the world, or is it genuinely like that? And if some new mathematics were to be discovered?
No, it is genuinely like that. It is independent of the way you measure it. I mean, the uncertainty principle is mathematically equivalent to the kind of Nyquist-like criterion or this sampling bound that one has, but and the underlying mathematics is similar because it's coming from the Fourier transform. But by now we have a number of experiments which actually tell you that there is a underlying uncertainty which you can choose to see it in this way, but it's a fundamental uncertainty, and that's why there's a Planck's constant always over there. So at least as far as we have managed to understand things, and in physics it's always, you have to say that because you never know the next layer of what you might discover. But to the extent to which we have to the limits, as I said, even a billionth of the size of an atom, we have explored quantum effects very precisely, and it's completely in consonance with what you predict. So the wave particle nature seems to be an underlying the duality between waves and particles seems like a very fundamental nature part of reality.
In today's world, what are the different areas where physicists are really working on?
Of course, that's a very wide canvas. I mean, there are physicists. I spoke about only a very small part, if you wish, of the physics enterprise. There's particle physics exploring the very, very small. I mentioned some of the other interactions of nature, and I showed this picture of this collider in Geneva. So that is describing some of the other interactions, electromagnetism, the strong interactions, the nuclear interactions, the weak interactions. And there are many particles, fundamental particles. There's a sort of a model called the standard model by which we understand the fundamental building blocks and their interactions. But whether that's the full story, people are trying to explore that. There are additional forces operating at even smaller levels. Are these there or not? Are there additional particles? Whether there is something called unification of all these forces. So these are other areas which are also very active. And there's the very large, as I said, in terms of black holes, gravity, but more generally cosmology, which the plots that I showed you of the cosmic microwave background and the distribution of galaxies, those are part of the experimental cosmologists are now doing, and which has made cosmology a precise science in the last 2 decades, understanding the evolution of the universe, starting from tiny quantum fluctuations, the detailed evolution through the formation of the first stars and the galaxies and and so on. It's a very detailed picture we are building up of the history of the universe. But to understand the very origin, you need to know, to have a real theory of quantum gravity, which string theory and so on is trying to do. Then, of course, I didn't mention it all, but there is so-called condensed matter physics, which is studying the properties of many materials and things you find in nature, or new materials that you might discover, which you might have heard of high temperature superconductors, nanomaterials, quantum dots. All these sort of things are all part of the exploration of the whole new kinds of physics that when many particles come together, how they can behave. So that's, so if I said very, very small and very, very large, there's also the very, very complex. So complex systems, how they behave, that's another frontier of our knowledge, which I didn't touch upon at all over here, but so that's, there are many things. As I said, even quantum information, quantum computation is a very active area. There are even companies like Microsoft and Google which are trying to build a quantum computer because perhaps there is some reason to believe that computers built on quantum principles might actually do things faster. Might be, if you had a quantum computer, the usual RSA algorithm for cryptography would be broken much faster. So you would need to develop new tools. So there's many areas like that, and it's physics is certainly very on different fronts. It is expanding our understanding.
So please explain how we can visualize singularity.
It's very difficult. It's like maybe one way is if you imagine like a tip of a cone. That is a place where the curvature is sort of is kind of localized. It's very highly pointed. That's a simple example of a singularity. So that's called a conical singularity, in fact. So if I have just an ice cream cone and a very sharp idealized cone with a point, and then you can think of that as a singularity. And in space, at least in space-time, it's more difficult to visualize, but at least that may give you an idea.
I have one question. In your lecture, you told that black hole origin will increase, right? So then, what is at the end of the black hole when black hole dies? So how
no, black hole would okay. It's in a sense an important question. So that statement that I said was at the classical level. In Einstein's theory, black hole area will just keep increasing, and because it will just keep swallowing up things. It doesn't die in a conventional sense like a star dies. A star dies because it can no longer burn its fuel, and then it collapses and forms a black hole. So at least in Einstein's theory, once a black hole is formed, it would just remain like that. But what Hawking found was if you include the quantum effects, the black hole can radiate. But when you radiate, you're actually losing energy. So if you wait for an extremely long time, which will be probably much longer than the age of the universe, the black hole will eventually evaporate, like a hot body evaporates. At least it will come to equilibrium with the cosmic microwave background temperature. So all the radiation will go off, and there will be nothing left. It will be just a radiation. So in that sense, the entropy of the black hole would have been converted to the entropy in the radiation, electromagnetic. But that's, you have to wait exponentially long time for that to happen. So that would be the ultimate fate of the black hole.
But another thing, that temperature analogy what you draw, that is from the entropy principle and that general theory of relativity principle. But that is not an exact temperature, right?
It is an exact temperature.
It's an
that is
analogy.
no. That is what Hawking found. Initially, he thought it was an analogy, but then he found that a black body, a black hole, actually has a temperature of that value. That's why it has a h bar. You can calculate what if I give you the black hole that LIGO discovered, I can tell you what its temperature should be. It's a minuscule temperature. It's not a temperature we can, at least in current day, this thing measure or see directly, but it is there. It is supposed to be a non-zero temperature, and that's why it radiates. And we understand now the process also much better after Hawking's original derivation. So Hawking, in fact, felt that it was only an analogy, and he tried to show that there is no way it can radiate, but he actually did the calculation and he found that it actually radiates. So he was actually initially, if you read his book, you will see he says that I didn't know what to make of it, and I thought that this is some mistake or something, but it's actually there, and now we understand in multiple ways, and it's a real effect. So, which is why it's called Hawking radiation and the Hawking temperature. And so it's more than an analogy.
I have a quick question to do with the Higgs boson here. Two things really. One is, I remember Mr. Hawking saying that physics would be more exciting if the Higgs boson wasn't discovered. That I didn't quite understand. I don't know if you can throw light on that. And the other thing is, when we talk about the mass of an object, we always thought it came from neutrons and protons. But how does this God particle actually trigger mass on something? I didn't quite get that concept.
Yeah, so firstly, I think Hawking said this probably before the Higgs boson was discovered. Now we have the Higgs boson, so that's the reality. I think what he meant by that was that physics is always challenged when you find something new and surprising. Higgs boson was what was expected. That was the sort of expected prediction, and you found it. So there was no surprise that way. So it kind of closed a chapter in our understanding of physics. But physics always thrives on paradox or something very novel. That is what is then telling you that something new is around the corner, like this temperature and so on. So that's the sense in which I think he was probably meaning when he's saying that it would be more exciting, because then you would have a real puzzle to try to solve. Oh, why is the Higgs boson not there, and yet you have many of the phenomena which give mass? Because the Higgs mechanism is a way to give mass. But it's true, and this is something that is a little misleadingly put in the usual popular science literature, that Higgs boson gives all the mass, but it is true that most of the mass that we see is from protons and neutrons, which get its mass mainly from the binding of the quarks, and so it's not from the Higgs boson per se. What the Higgs boson gives mass to are the electrons, which are very light compared to the protons and neutrons. So the Higgs mechanism is a way of giving mass to the to the electrons and their cousins, and also the quarks. But most of the energy of the protons and neutrons really comes from the binding energy of the attractive energy of the quarks, and not so much from the mass of the quarks themselves. So, yeah.
Yeah, I think we are at 6:30. I know we can go on for a long time. It's a very interesting topic, and but all good things come to an end. So we will stop the Abhishek program here. If the professor has more time, maybe you can have questions offline. I think he may be able to spend a few more minutes. On behalf of our club and everyone here.
It was my pleasure.